हेलो एवरीवन, वंस अगेन वेलकम टू आवर चैनल बीट द नीट। एंड कैसे हैं आप सब लोग? एंड आई होप कि आप सभी लोग बहुत ही अच्छे होंगे, सेहतमंद होंगे और बहुत अच्छी तरह से अपनी तैयारी कर रहे होंगे। टुडे इज 15th ऑफ अगस्त एंड हैप्पी इंडिपेंडेंस डे टू ऑल ऑफ यू। एंड आई होप कि आप सभी लोग अपनी तैयारी को इतने अच्छे से कर रहे होंगे कि आप सभी का सिलेक्शन फर्स्ट टाइम जो आपका अटेम्प्ट आप देने जा रहे हैं नीट 2024 में, तो आप उस अटेम्प्ट में अपने सिलेक्शन को क्लियर कर लेंगे। एंड मैं आप लोगों के लिए फिजिक्स ऑडियो बुक का जो प्रोजेक्ट चल रहा था, मैंने उसको वापस से कंटिन्यू कर दिया है। तो आज मैं आप लोगों के साथ में चैप्टर 11 ड्यूअल नेचर ऑफ रेडिएशन एंड मैटर बनाऊंगी। एंड कल मैंने आप लोगों के लिए एटम्स वाला चैप्टर रिकॉर्ड करके ऑलरेडी अपलोड कर दिया है, तो जिन बच्चों ने नहीं देखा है तो जल्दी से जाइए देख लीजिए, डिस्क्रिप्शन में मैंने उसका लिंक दे दिया है। एंड जो बच्चे नए हैं मेरे चैनल पे, अगर आपको नहीं पता है तो मैं आपको बता दूं कि आप मेरे चैनल पे ढेर सारी ऑडियो बुक सुन सकते हैं, सारे सब्जेक्ट्स की अवेलेबल हैं। एंड साथ ही साथ आप ढेर सारे क्वेश्चंस की प्रैक्टिस कर सकते हैं अगर आप मेरी कम्युनिटी को चेक करते हैं, क्योंकि मैं डेली आप लोगों के लिए कम्युनिटी पोस्ट करती हूँ जिसमें आपको एक पर्टिकुलर टाइम के बाद में क्वेश्चन मिलता है जिसे आप लोग देख सकते हैं। एंड मैं रेगुलरली आप लोगों के लिए वीडियोस बना रही हूँ, टीचिंग वीडियोस, माइंड मैप, ऑडियो बुक्स एंड बहुत सारे क्वेश्चन प्रैक्टिस। एंड जो बच्चे टेलीग्राम चैनल पे नहीं हैं तो बेटा जी ज्वाइन कर लीजिए, क्योंकि मैं टेलीग्राम चैनल पे आप लोगों के लिए क्वेश्चंस, नोट्स, माइंड मैप, बहुत सारी चीज़ें शेयर करती रहती हूँ। तो उसका लिंक भी मैंने डिस्क्रिप्शन में दे दिया है। तो चलिए ज़्यादा बात नहीं करते हैं और जल्दी से शुरू करते हैं हम अपने चैप्टर को, दैट इज़ द ड्यूअल नेचर ऑफ रेडिएशन एंड मैटर। एंड जैसे कि आपने मुझे इस वीडियो में बताया, ठीक उसी तरह से आप लोगों को मुझे बताना है कि मैम मुझे ये वाली ऑडियो बुक पहले चाहिए। जो बच्चे हिंदी के लिए रिक्वेस्ट कर रहे हैं तो बेटा जी हिंदी की ऑडियो बुक बनाना, बायोलॉजी के लिए तो फिर भी पॉसिबल था, बट केमिस्ट्री एंड फिजिक्स के लिए इट्स बहुत ज़्यादा तो नहीं, लेकिन हाँ थोड़ा डिफिकल्ट है, बट आई विल ट्राई, है ना। तो थोड़ा सा मुझे आप लोग टाइम दीजिए। तो मैं एक बार जैसे ही आप लोगों का ये न्यू एनसीईआरटी और ये सारी चीज़ें कंप्लीट कर रही हूँ तो पैरेलल मुझे जैसे ही टाइम मिलता है आई विल ट्राई टू मेक ऑडियो बुक्स इन हिंदी ऑल्सो। बाकी तब तक आप लोग बायोलॉजी की जो मैंने हिंदी में ऑडियो बुक बना रखी है उनको आप सुन सकते हैं। एंड जल्दी मैं आप लोगों की न्यू एनसीईआरटी की भी बायोलॉजी हिंदी की ऑडियो बुक, जिन चैप्टर्स में चेंजेस आए हैं उनकी मैं प्रिपेयर करके आप लोगों के साथ में शेयर करूँगी। साथ ही साथ में मैं टीचिंग वीडियोस भी जो शेयर कर रही हूँ वो भी आप जा कर के देख सकते हैं और आप टॉपिक वाइज उनको प्रिपेयर कर सकते हैं, क्योंकि मैं जो वीडियोस आपके लिए बना रही हूँ उसमें मैं सिर्फ आपको पढ़ा नहीं रही हूँ, उस पर्टिकुलर टॉपिक से क्या क्वेश्चंस पूछे गए थे वो मैं आप लोगों को साथ ही साथ शेयर करती हूँ, ताकि आप लोगों को पता चल जाए कि इस टॉपिक में से ये क्वेश्चंस पूछे जा रहे हैं, तो आप फोकस होकर के उन पर ही मेहनत करें, क्योंकि स्मार्ट वर्क की ज़रूरत है, हार्ड वर्क की नहीं। तो चलिए, ढेर सारे प्यार की उम्मीद करती हूँ इस ऑडियो बुक के लिए आप लोगों से। एंड स्टार्ट करते हैं 11.1 इंट्रोडक्शन। The Maxwell's equation of electromagnetism and Hertz's experiment on the generation and detection of electromagnetic waves in 1887 strongly established the wave nature of light. Towards the same period, at the end of 19th century, experimental investigations on conduction of electric discharge through gases at low pressure in a discharge tube led to many historic discoveries. The discovery of X-rays by Roentgen in 1895 of electron by J.J. Thomson in 1897 were important milestones in the understanding of atomic structure. It was found that at sufficiently low pressure of about 0.001 mm of mercury column, a discharge took place between the two electrodes on applying the electric field to the gas in the discharge tube. A fluorescent glow appeared on the glass opposite to cathode. The color of glow of the glass depended on the type of glass, it being yellowish green for soda glass. The cause of this fluorescence was attributed to the radiation which appeared to be coming from the cathode. These cathode rays were discovered in 1870 by William Crookes, who later in 1879 suggested that these rays consisted of streams of fast-moving negatively charged particles. The British physicist J.J. Thomson, 1856 to 1940, confirmed this hypothesis. By applying mutually perpendicular electric and magnetic fields across the discharge tube, J.J. Thomson was the first to determine experimentally the speed and the specific charge to mass ratio E upon m of the cathode ray particles. They found to travel with speeds ranging from 0.1 to 0.2 times the speed of light, that is the 3 into 10 to the power meter per second. The presently accepted value of E upon m is 1.76 into 10 to the power 11, and further the value of E upon m was found to be independent of the nature of the metal used as the cathode or the gas introduced in the discharge tube. This observation suggested the universality of cathode ray particles. Around the same time, in 1887, it was found that certain metals, when irradiated by ultraviolet light, emitted negatively charged particles having small speeds. Also, certain metals, when heated to a high temperature, were found to emit negatively charged particles. The value of E upon m of these particles was found to be same as that of cathode ray particles. These observations thus established that all these particles, although produced under different conditions, were identical in nature. J.J. Thomson in 1897 named these particles as electrons and suggested that they were fundamental universal constituents of matter. For his epoch-making discovery of electron, through his theoretical and experimental investigations on conduction of electricity by gases, he was awarded the Nobel Prize in Physics in 1906. In 1913, the American physicist R.A. Millikan performed the pioneering oil drop experiment for the precise measurement of the charge on an electron. He found that the charge on an oil droplet was always an integral multiple of an elementary charge 1.602 into 10 to the power minus 19 coulomb. Millikan's experiment established that electric charge is quantized. From the value of charge and a specific charge, the mass of the electron could be determined. 11.2 Electron emission. We know that metals have free electrons, negatively charged particles, that are responsible for their conductivity. However, the free electrons cannot normally escape out of the metal surface. If an electron attempts to come out of the metal surface acquires a positive charge and pulls the electron back to the metal. The free electron is thus held inside the metal surface by the attractive forces of the ions. Consequently, the electron can come out of the metal surface only if it has got sufficient energy to overcome the attractive pull. A certain minimum amount of energy is required to given to an electron to pull it out from the surface of the metal. This minimum energy required by an electron to escape from the metal surface is called the work function of the metal. It is generally denoted by phi naught and measured in electron volt. Once electron volt is the energy gained by an electron when it has been accelerated by a potential difference of 1 volt, so that 1 electron volt is 1.602 into 10 to the power minus 19 joule. This unit of energy is commonly used in atomic and nuclear physics. The work function depends on the properties of the metal and the nature of its surface. The values of work function of some metals are given in table 11.1. These values are approximate as they are very sensitive to surface impurities. Note from table 11.1 that the work function of platinum is the highest, phi naught is equals to 5.65 electron volt, while it is the lowest, phi naught is equals to 2.14 electron volt for cesium. The minimum energy required for the electron emission from the metal surface can be supplied to the free electron by any one of the following physical processes. Table 11.1 work function of some metals. Okay, so metals भी दी हैं and their work function values दी हैं, let me read that. Cesium 2.14, potassium 2.30, sodium 2.75, calcium 3.20, molybdenum 4.17, lead 4.25, aluminium 4.28, mercury 4.49, copper 4.65, silver 4.70, nickel 5.15 and platinum 5.65. So finally आप revise कर लेंगे. Number 1, thermionic emission. But suitably heating sufficient thermal energy can be imparted to the free electrons to enable them to come out of the metal. Number 2, field emission by applying a very strong electric field of the order of 10 to the power 8 and Vm to the power minus 1 volt per meter to a metal, electrons can be pulled out of the metal as in a spark plug. Third, photoelectric emission. When a light is of suitable frequency illuminates a metal surface, electrons are emitted from the metal surface. These photo or light generated electrons are called photoelectrons. 11.3 Photoelectric effect. 11.3.1 Hertz observations. The phenomena of photoelectric emission was discovered in 1887 by Heinrich Hertz 1857 to 1894 during his electromagnetic wave experiments. In his experimental investigation on the production of electromagnetic waves by means of a spark discharge, Hertz observed that high voltage sparks across the detector loop were enhanced when the emitter plate was illuminated by ultraviolet light from an arc lamp. Light shining on the metal surface somehow facilitated the escape of free charged particles, which now know as electrons. When light falls on a metal surface, some electrons near the surface absorb enough energy from the incident radiation to overcome the attraction of the positive ions in the material of the surface. After gaining sufficient energy from the incident light, the electrons escape from the surface of the metal into the surrounding space. 11.3.2 Holbach's and Lenard's observation. Wilhelm Holbach and Philip Lenard investigated the phenomena of photoelectric emission in detail during 1886 to 1902. Lenard observed that when ultraviolet radiations were allowed to fall on emitter plate of an evacuated glass tube enclosing two electrodes, metal plates, current flows in the circuit. As soon as the ultraviolet radiations were stopped, the current flow also stopped. These observations indicate that ultraviolet radiation fall on emitter plate C. Electrons are ejected from it, which are attracted towards the positive collector plate A by the electric field. The electrons flow through the evacuated glass tube, resulting in the current flow. Thus, light falling on the surface of the emitter causes current in the external circuit. Holbach and Lenard studied how this photocurrent varied with collector plate potential and with frequency and intensity of incident light. Holbach in 1888 undertook the study further and connected a negatively charged zinc plate to an electroscope. He observed that the zinc plate lost its charge when it was illuminated by ultraviolet light. Further, the uncharged zinc plate became positively charged when it was irradiated by ultraviolet light. Positive charge on a positively charged zinc plate was found to be further enhanced when it was illuminated by ultraviolet light. From these observations, he concluded that negatively charged particles were emitted from the zinc plate under the action of ultraviolet light. After the discovery of the electron in 1897, it became evident that the incident light causes electrons to be emitted from the emitter plate. Due to negative charge, the emitted electrons are pushed towards the collector plate by the electric field. Holbach and Lenard also observed that when ultraviolet light fell on the emitter plate, no electrons were emitted at all when the frequency of the incident light was smaller than a certain minimum value, called the threshold frequency. This minimum frequency depends on the nature of the material of the emitter plate. It was found that certain metals like zinc, cadmium, magnesium, etc. responded only to ultraviolet light, having short wavelength, to cause electron emission from the surface. However, some alkali metals such as lithium, sodium, potassium, cesium and rubidium were sensitive even to visible light. All these photosensitive substances emit electrons when they are illuminated by light. After the discovery of electrons, these electrons were termed as photoelectrons and the phenomena is called photoelectric effect. 11.4 Experimental study of photoelectric effect. Figure 11.1 depicts a schematic view of the arrangement used for the experimental study of photoelectric effect. It consists of an evacuated glass or quartz tube having a photosensitive plate C and another metal plate A. Monochromatic light from the source S of sufficiently short wavelength passes through the window W and falls on the photosensitive plate C emitter. A transparent quartz window is sealed on the glass tube, which permits ultraviolet radiation to pass through it and irradiate the photosensitive plate C. The electrons are emitted by the plate C and are collected by the plate A collector by the electric field created by the battery. The battery maintains the potential difference between the plate C and A that can be varied. The polarity of plate C and A can be reversed by a commutator. Thus, the plate A can be maintained at a desired positive or negative potential with respect to emitter C. When the collector plate A is positive with respect to the emitter plate C, the electrons are attracted to it. The emission of electrons causes flow of electric current in the circuit. The potential difference between the emitter and collector plates is measured by a voltmeter, whereas the resulting photocurrent flowing in the circuit is measured by microammeter. The photoelectric current can be increased or decreased by varying the potential of collector plate A with respect to the emitter plate C. The intensity and frequency of the incident light can be varied, as can the potential difference V between the emitter C and the collector A. We can use the experimental arrangement of figure 11.1. Here is the figure. See this diagram. आई होप कि आप लोग NCERT बुक लेकर के बैठते होंगे जब आप ये ऑडियो बुक सुनते हैं, क्योंकि दैट इज़ द बेस्ट वे टू लिसन द ऑडियो बुक. आप बिल्कुल डिस्ट्रैक्ट नहीं होंगे, सारी चीज़ें आप पढ़ते जाएंगे, आपको रिवीजन बहुत फास्ट मैनर में होगा. फॉर एवरी सब्जेक्ट आई एम टेलिंग यू, फॉर बायोलॉजी, केमिस्ट्री, फिजिक्स, एवरी सब्जेक्ट. Figure 11.1 to study the variation of photocurrent with A. Intensity of radiation, B. Frequency of incident radiation, C. The potential difference between the plates A and C, and D. The nature of material of plate C. Light of different frequencies can be used by putting appropriate colored filter or colored glass in the path of light falling on the emitter C. The intensity of light is varied by changing the distance of the light source from the emitter. 11.2 diagram is also here, ये अभी आगे आएगा. 11.4.1 Effect of intensity of light on photocurrent. The collector A is maintained at a positive potential with respect to the emitter C, so that electrons ejected from C are attracted towards collector A. Keeping the frequency of the incident radiation and the accelerating potential fixed, the intensity of light is varied and the resulting photoelectric current is measured each time. It is found that the photocurrent increases linearly with intensity of incident light, as shown graphically in figure 11.2. The photocurrent is directly proportional to the number of photoelectrons emitted per second. This implies that the number of photoelectrons emitted per second is directly proportional to the intensity of incident radiation. 11.4.2 Effect of potential on photoelectric current. We first keep the plate A at some positive accelerating potential with respect to the plate C and illuminate the plate C with light of fixed frequency and fixed intensity. We next vary the positive potential of plate A gradually and measuring the resulting photocurrent each time. It is found that the photoelectric current increases with increase in accelerating positive potential. At some stage, for a certain positive potential of plate A, all the emitted electrons are collected by the plate A and the photoelectric current becomes maximum or saturates. If we increase the accelerating potential of plate A further, the photocurrent does not increase. This maximum value of photoelectric current is called saturation current. Saturation current corresponds to the case when all photoelectrons emitted by the emitter plate C reach the collector plate A. We now apply a negative or retarding potential to the plate A with respect to the plate C and make it increasingly negative gradually. When the polarity is reversed, the electrons are repelled and only the most energetic electrons are able to reach the collector A. The photocurrent is found to decrease rapidly until it drops to zero at a certain sharply defined critical value of the negative potential V0 on the plate A. For a particular frequency of incident radiation, the minimum negative potential given to the plate A, for which the photocurrent stops or becomes zero, is called the cutoff or stopping potential. The interpretation of the observation in terms of photoelectrons is straightforward. All the photoelectrons emitted from the metal do not have the same energy. Photoelectric current is zero when the stopping potential is sufficient to repel even the most energetic photoelectrons with the maximum kinetic energy Kmax, so that Kmax is equals to EV0. We can now repeat the experiment with incident radiation of the same frequency but the higher intensity I2 and I3. I3 is greater than I2 is greater than I1. We note that the saturation currents are now found to be at higher values. This shows that more electrons are being emitted per second, proportional to the intensity of incident radiation. But the stopping potential remains the same as that for the incident radiation of intensity I1, as shown graphically in figure 11.3. So here is the diagram 11.3. Thus, for a given frequency of the incident radiation, the stopping potential is independent of its intensity. In other words, the maximum kinetic energy of photoelectrons depends on the light source and the emitter plate material, but is independent of intensity of incident radiation. 11.4.3 Effect of frequency of incident radiation on stopping potential. 11.4 diagram is here. We now study the relation between the frequency of the incident radiation and the stopping potential V naught, we suitably adjust the same intensity of light radiation at various frequencies and study the variation of photocurrent with collector plate potential. The resulting variation is shown in figure 11.4. We obtain different values of stopping potential but the same value of saturation current for incident radiation of different frequencies. The energy of the emitted electrons depends on the frequency of the incident radiations. The stopping potential is more negative for higher frequency of incident radiation. Note from figure 11.4 that the stopping potential are in the order V03 is greater than V02 is greater than V01. If the frequencies are in the order mu3 is greater than u2 is greater than u1, this implies that greater the frequency of incident light, greater is the maximum kinetic energy of the photoelectrons. Consequently, we need greater retarding potential to stop them completely. If we plot a graph between the frequency of incident radiation and the corresponding stopping potential for different metals, we get a straight line as shown in figure 11.5. Here is a diagram. Number 1. The graph shows that the stopping potential V naught varies linearly with the frequency of incident radiation for a given photosensitive material. Number 2. There exists a certain minimum cutoff frequency nu naught for which the stopping potential is 0. These observations have two implications. Number 1. The maximum kinetic energy of the photoelectrons varies linearly with the frequency of incident radiation but is independent of its intensity. Number 2. For a frequency nu of incident radiation lower than the cutoff frequency nu naught, no photoelectric emission is possible even if the intensity is large. This minimum cutoff frequency nu naught is called the threshold frequency. It is different for different metals. Different photosensitive metals respond differently to light. Selenium is more sensitive than zinc or copper. The same photosensitive substance gives different response to light of different wavelengths. For example, ultraviolet light gives rise to photoelectric effect in copper while green or red light does not. Note that in all the above experiments, it is found that if frequency of the incident radiation exceeds the threshold frequency, the photoelectric emission starts instantaneously without any apparent time lag, even if the incident radiation is very dim. It is now known that emission starts in a time of the order of 10 to the power minus 9 seconds or less. We now summarize the experimental features and observations. Number 1. For a given photosensitive material and frequency of incident radiation above the threshold frequency, the photoelectric current is directly proportional to the intensity of incident light. Number 2. For a given photosensitive material and frequency of incident radiation, saturation current is found to be proportional to the intensity of incident radiation, whereas the stopping potential is independent of its intensity. Number 3. For a given photosensitive material, there exists a certain minimum cutoff frequency of the incident radiation, called the threshold frequency, below which no emission of photoelectron takes place. No matter how intense the incident light is above the threshold frequency, the stopping potential or equivalently the maximum kinetic energy of the emitted photoelectrons increases linearly with the frequency of the incident radiation, but is independent of its intensity. Fourth, the photoelectric emission is an instantaneous process without any apparent time lag, 10 to the power minus 9 seconds or less, even when the incident radiation is made exceedingly dim. 11.5. Photoelectric effect and wave theory of light. The wave nature of light as well as established by the end of the 19th century. The phenomena of interference, diffraction and polarization were explained in a natural and satisfactory way by the wave picture of light. According to this picture, light is an electromagnetic wave consisting of electric and magnetic fields with continuous distribution of energy over the region of space over which the wave is extended. Let us now see if this wave picture of light can explain the observations on photoelectric emission given in the previous section. According to the wave picture of light, the free electrons at the surface of the metal over which the beam of radiations falls absorb the radiant energy continuously. The greater the intensity of radiation, the greater are the amplitude of electric and magnetic fields. Consequently, the greater the intensity, the greater should be the energy absorbed by each electron. In this picture, the maximum kinetic energy of photoelectrons on the surface is then expected to increase with increase in intensity. Also, no matter what the frequency of radiation is, a sufficiently intense beam of radiation over sufficient time should be able to impart enough energy to the electrons so that they exceed the minimum energy needed to escape from the metal surface. A threshold frequency therefore should not exist. These expectations of the wave theory directly contradict observations number 1, number 2 and number 3 given at the end of the subsection 11.4.3. Already we have read. Further, we should note that in the wave picture, the absorption of energy by electron takes place continuously over the entire wavefront of the radiation. Since a large number of electrons absorb energy, the energy absorbed per electron per unit time turns out to be small. Explicit calculation estimate that it can take hours or more for a single electron to pick up sufficient energy to overcome the work function and come out of the metal. This conclusion is gained in a striking contrast to observation that the photoelectric emission is instantaneous. In short, the wave picture is unable to explain the most basic feature of photoelectric emission. 11.6 Einstein's photoelectric equation, energy quantum of radiation. In 1905, Albert Einstein (1879 to 1955) proposed a radically new picture of electromagnetic radiation to explain photoelectric effect. In this picture, photoelectric emission does not take place by continuous absorption of energy from radiation. Radiation energy is built up of discrete units, the so-called quanta of energy of radiation. Each quantum of radiant energy has energy h nu. Here h is the Planck's constant and nu frequency of the light. In photoelectric effect, an electron absorbs a quantum energy h nu of radiation. If this quantum of energy absorbed exceeds the minimum energy needed for the electron to escape for the metal surface work function phi naught. The electron is emitted with the maximum kinetic energy K max is equals to h nu minus phi naught. More tightly bound electrons will emerge with kinetic energies less than the maximum value. Note that the intensity of light of a given frequency is determined by the number of photons incident per second. Increasing the intensity will increase the number of emitted electrons per second. However, the maximum kinetic energy of the emitted photoelectrons is determined by the energy of each photon. Equation 11.2 is known as Einstein's photoelectric equation. We now see how this equation accounts in a simple and elegant manner all the observations on photoelectric effect given at the end of subsection 11.4.3. According to equation 11.2, K max depends linearly on nu and is independent of intensity of radiation. In agreement with the observation, this has happened because in Einstein's picture, photoelectric effect arises from the absorption of a single quantum of radiation by a single electron. The intensity of radiation that is proportional to the number of energy quanta per unit area per unit time is irrelevant to the basic process. Since K max must be non-negative, equation 11.2 implies that photoelectric emission is possible only if h nu is greater than phi naught, or nu is greater than nu naught, where nu naught is equals to phi naught upon h. Equation 11.3 shows that the greater the work function phi naught, the higher the minimum or threshold frequency nu naught needed to emit photoelectrons. Thus, there exists a threshold frequency nu naught for the metal surface, below which no photoelectric emission is possible, no matter how intense the incident radiation may be or how long it falls on the surface. In this picture, intensity of radiation as noted above is proportional to the number of energy quanta per unit area per unit time. The greater the number of energy quanta available, the greater is the number of electrons absorbing the energy quanta and greater. Therefore is the number of electrons coming out of the metal. This explains why for nu is greater than nu naught, photoelectric current is proportional to intensity. Third, in Einstein's picture, the basic elementary process involved in photoelectric effect is the absorption of light quantum by an electron. This process is instantaneous, thus whatever may be the intensity, that is the number of quanta of radiation per unit area per unit time. Photoelectric emission is instantaneous. Low intensity does not mean delay in emission, since the basic elementary process is the same. Intensity only determines how many electrons are able to participate in the elementary process, absorption of light, quantum by a single electron, and therefore the photoelectric current. Using equation 11.1, the photoelectric equation 11.2 can be written as, here you can see the equation. This is an important result. It predicts that V0 versus nu curve is a straight line with a slope h upon e, independent of the nature of the material. During 1906 to 16, Millikan performed a series of experiments on photoelectric effect aimed at disproving Einstein's photoelectric equation. He measured the slope of the straight line obtained for sodium similar to that shown in figure 11.5. Using the known value of E, he determined the value of Planck's constant h. This value was close to the value of Planck's constant 6.626 into 10 to the power minus 34 joule second, determined in an entirely different context. In this way, in 1916, Millikan proved that validity of Einstein's photoelectric equation instead of disproving it. The successful explanation of photoelectric effect using the hypothesis of light quanta and the experimental determination of value of h and phi naught in agreement with values obtained from other experiments led to the acceptance of Einstein's picture of photoelectric effect. Millikan verified photoelectric equation with great precision for a number of alkali metals over a wide range of radiation frequencies. Here are the information about Albert Einstein. Albert Einstein, 1879-1955, Einstein, one of the greatest physicists of all time, was born in Ulm, Germany. In 1905, he published 3 path-breaking papers. In the first paper, he introduced the notion of light quanta, now called photons, and used it to explain the features of photoelectric effect. In the second paper, he developed a theory of Brownian motion, confirmed experimentally a few years later, and provided a convincing evidence of the atomic picture of matter. The third paper gave birth to the special theory of relativity. In 1916, he published the general theory of relativity. Some of Einstein's most significant later contributions are the notion of stimulated emission introduced in an alternative derivation of Planck's black body radiation law, static model of the universe which started modern cosmology, quantum statistics of a gas of a massive bosons, and a critical analysis of the foundation of quantum mechanics. In 1921, he was awarded the Nobel Prize in Physics for his contribution to theoretical physics and the photoelectric effect. 11.7 Particle nature of light, the photon. Photoelectric effect thus gave evidence to the strange fact that light in interaction with matter behaved as if it was made of quanta or packets of energy, each of energy h nu. Is the light quantum of energy to be associated with a particle? Einstein arrived at the important result that the light quantum can also be associated with momentum. A definite value of energy as well as momentum is a strong sign that the light quantum can be associated with particle. This particle was later named photon. The particle-like behavior of light was further confirmed in 1924 by the experiment of A. H. Compton 1892 to 1962 on scattering of X-rays from electrons. In 1921, Einstein was awarded the Nobel Prize in Physics for his contribution to theoretical physics and the photoelectric effect. In 1923, Millikan was awarded the Nobel Prize in Physics for his work on the elementary charge of the electricity and on the photoelectric effect. We can summarize the photon picture of electromagnetic radiation as follows. Number 1. In interaction of radiation with matter, radiation behaves as if it is made up of particles called photons. Number 2. Each photon has energy E equals to h nu and momentum p and speed c, the speed of light. Third, all photons of light of a particular frequency nu or wavelength lambda wave have the same energy E and momentum p, whatever the intensity of radiation may be. By increasing the intensity of light of given wavelength, there is only an increase in the number of photons per second crossing a given area, with each photon having the same energy. This photon energy is independent of intensity of radiation. Fourth, photons are electrically neutral and are not deflected by electric and magnetic fields. Fifth, In a photon particle collision, the total energy and total momentum are conserved. However, the number of photons may not be conserved in a collision. The photon may be absorbed or a new photon may be created. Here is the examples. 11.8 Wave nature of matter. The dual nature of light, electromagnetic radiation in general, comes out clearly from what we have learned in this and the preceding chapters. The wave nature of light shows up in the phenomena of interference, diffraction and polarization. On the other hand, in photoelectric effect and Compton effect, which involve energy and momentum transfer, radiation behaves as if it is made up of a bunch of particles, the photons. Whether a particle or wave description is best suited for understanding an experiment depends on the nature of the experiment. For example, in the familiar phenomena of seeing an object by our eye, both descriptions are important. The gathering and focusing mechanism of light by the eye lens is well described in the wave picture, but its absorption by the rods and cones of the retina requires the photon picture of light. A natural question arises: if radiation has a dual wave particle nature, might not be the particle of nature, the electrons, protons, etc., also exhibit wave-like character? In 1924, the French physicist Louis Victor de Broglie, pronounced as de Broglie, 1892 to 1987, put forward the bold hypothesis that moving particles of matter should display wave-like properties under suitable conditions. He reasoned that nature was symmetrical and that the two basic physical entities, matter and energy, must have symmetrical character. If radiation shows dual aspects, so should matter. De Broglie proposed that wavelength lambda associated with a particle of momentum p is given as lambda is equals to h upon p is equals to h upon mv, where m is the mass of the particle and v its speed. Equation 11.5 is known as the de Broglie relation, and wavelength lambda of the matter wave is called de Broglie wavelength. The dual aspect of matter is evident in the de Broglie relation. On the left hand side of equation, lambda is the attribute of a wave, while on the right hand side the momentum p is a typical attribute of a particle. Planck's constant h relates the two attributes. Equation 11.5 for a material particle is basically a hypothesis whose validity can be tested only by experiment. However, it is interesting to see that it is satisfied also by a photon, for a photon as we have seen. However, it is interesting to see that it is satisfied also by a photon. For a photon as we have seen, p is equals to h nu upon c, and therefore you can see the h upon p value is equals to lambda. That is the de Broglie wavelength of a photon given by equation 11.5 equals the wavelength of electromagnetic radiation of which the photon is a quantum of energy and momentum. Clearly from equation 11.5, lambda is smaller for a heavier particle or more energetic particle. For example, the de Broglie wavelength of a ball of mass 0.12 kg moving with a speed of 20 meter per second is easily calculated, and here is the complete calculation. And let's read this photocell. A photocell is a technological application of the photoelectric effect. It is a device whose electrical properties are affected by light. It is also sometimes called an electric eye. A photocell consists of a semi-cylindrical photosensitive metal plate C and a wire loop, a collector supporter in an evacuated glass or quartz bulb. It is connected to the external circuit having a high tension battery B and micrometer as shown in the figure. Sometimes instead of the plate C, a thin layer of photosensitive material is pasted on the inside of the bulb. A part of the bulb is left clean for the light to enter it. When light of suitable wavelength falls on the emitter C, photoelectrons are emitted. These photoelectrons are drawn to the collector. A photocurrent of the order of a few microampere can be normally obtained from a photocell. A photocell converts a change in intensity of illumination into a change in photocurrent. This current can be used to operate control systems and in light measuring devices. A photocell of lead sulfide sensitive to infrared radiation is used in electronic ignition circuits. In scientific work, photocells are used whenever it is necessary to measure the intensity of light. Light meters in photographic cameras make use of photocells to measure the intensity of incident light. The photocells inserted in the door light electric circuit are used as automatic door opener. A person approaching a doorway may interrupt a light beam which is incident on a photocell. The abrupt change in photocurrent may be used to start a motor which opens the door or rings an alarm. They are used in the control of a counting device which records every interruption of the light beam caused by a person or object passing across the beam. So photocell help count the persons entering an auditorium, provided they enter the hall one by one. They are used for detection of traffic law defaulters. An alarm may be sounded whenever a beam of invisible radiation is intercepted. In burglar alarm, invisible ultraviolet radiation is continuously made to fall on a photocell installed at the doorway. A person entering the door interrupts the beam falling on photocell, and the abrupt change in photocurrent is used to start an electric bell ringing. In fire alarm, a number of photocells are installed at suitable places in a building. In the event of breaking out a fire, light radiations fall upon the photocells. This completes the electric circuit through an electric bell or a siren which starts operating as a warning signal. Photocells are used in the pre-production of sound and motion pictures and in the television cameras for scanning and telecasting scenes. They are used in industries for detecting minor flaws or holes in metal sheets. And this wavelength is so small that it is beyond the measurement. This is the reason why macroscopic objects in our daily life do not show wave-like properties. On the other hand, in the subatomic domain, the wave character of particles is significant and measurable. ये आपका जो इससे टॉपिक पहले वाला था फोटोसेल से उससे रिलेटेड है. Consider an electron accelerated from rest through a potential V. The kinetic energy K of the electron equals the work done on it by the electric field. Here you can see the complete solution, where V is the magnitude of accelerating potential in volts for a 120 volt accelerating potential. Equation 11.11 gives lambda is equals to 0.112 nm. This wavelength is of the same order as the spacing between the atomic planes in crystals. This suggests that matter waves associated with an electron could be verified by crystal diffraction experiments analogous to X-ray diffraction. We describe the experimental verification of the de Broglie hypothesis in the next section. In 1929, de Broglie was awarded the Nobel Prize in Physics for his discovery of the wave nature of electrons. The matter-wave picture elegantly incorporated the Heisenberg's uncertainty principle. According to this principle, it is not possible to measure both the position and momentum of an electron or any other particle at the same time exactly. There is always some uncertainty in the specification of position and some uncertainty in the specification of momentum. The product of delta x and delta p is of the order of h. Here you can see this new equation. Equation 11.12 allows the possibility that delta x is 0, but then delta p must be infinite in order that the product is non-zero. Similarly, if delta p is 0, delta x must be infinite. Ordinarily, both delta x and delta p are non-zero such that their product is of the order of h. Now, if an electron has a definite momentum p by the de Broglie relation, it has a definite wavelength lambda. A wave of definite single wavelength extends all over. Wave associated with the electron is not extended all over space. It is a wave packet extending over some finite region of space. In that case, delta x is not infinite but has some finite value depending on the extension of the wave pocket. Also, you must appreciate that a wave pocket of a finite extensions does not have single wavelength. It is built up of a wavelength spread around some central wavelength. By de Broglie's relation, then the momentum of the electron will have a spread and uncertainty delta p. This is as expected from the uncertainty principle. It can be shown that the wave packet description together with the de Broglie relation and Born's probability interpretation reproduce the Heisenberg's uncertainty principles exactly. In chapter 12, the de Broglie relation will be seen to justify Bohr's postulate on quantization of angular momentum of electron in an atom. Figure 11.6 shows a schematic diagram of a localized wave packet and B, an extended wave with fixed wavelength. Here something left. Yes, this is about the de Broglie. Louis Victor de Broglie, 1892-1987, French physicist who put forth a revolutionary idea of wave nature of matter. This idea was developed by Erwin Schrödinger into a full-fledged theory of quantum mechanics. commonly known as wave mechanics. In 1929, he was awarded the Nobel Prize in Physics for his discovery of the wave nature of electron. Now here is another example. Probability interpretation to matter waves. It is worth pausing here to reflect on just what a matter wave associated with a particle, say an electron, means. Actually, a truly satisfactory physical understanding of the dual nature of matter and radiation has not emerged so far. The great founders of quantum mechanics, Niels Bohr, Albert Einstein, and many others, struggled with this and related concepts for long. Still, the deep physical interpretation of quantum mechanics continues to be an area of active research. Despite this, the concept of matter wave has been mathematically introduced in modern quantum mechanism with great success. An important milestone in this connection was when Max Born suggested a probability interpretation to the matter wave amplitude. According to this, the intensity square of the amplitude of the matter wave at a point determines the probability density of particle at that point. Probability density means probability per unit volume. Thus, if the intensity of matter wave is large in certain region, there is a great probability of the particle being found there than where the intensity is small. Here is the next example. 11.9 Davison and Germer experiment. The wave nature of electrons was first experimentally verified by C.J. Davison and L.H. Germer in 1927 and independently by J.P. Thomson in 1928, who observed diffraction effects with beams of electrons scattered by crystals. Davison and Thomson shared the Nobel Prize in 1937 for their experimental discovery of diffraction of electrons by crystals. The experimental arrangement used by Davison and Germer is schematically shown in figure 11.7. It consists of an electron gun which comprises of a tungsten filament F coated with barium oxide and heated by a low voltage power supply. Electrons emitted by the filament are accelerated to a desired velocity by applying suitable potential voltage from a high voltage power supply. They are made to pass through a cylinder with fine holes along its axis, producing a fine collimated beam. The beam is made to fall on the surface of a naked crystal. The electrons are scattered in all directions by the atoms of the crystal. The intensity of the electron beam scattered in a given direction is measured by the electron detector. The detector can be moved on a circular scale and is connected to a sensitive galvanometer which records the current. The deflection of the galvanometer is proportional to the intensity of the electron beam entering the collector. The apparatus is enclosed in an evacuated chamber. By moving the detector on the circular scale at different positions, the intensity of the scattered electron beam is measured for different values of angle of scattering theta, which is the angle between the incident and the scattered electron beams. The variation of the intensity I of the scattered electrons with the angle of scattering theta is obtained for different accelerating voltages. The experiment was performed by varying the accelerating voltage from 44 volt to 68 volt. It was noticed that a strong peak appeared in the intensity of the scattered electron for an accelerating voltage of 54 volt at a scattering angle theta is equals to 50 degree. The appearance of the peak in a particular direction is due to the constructive interference of electrons scattering from different layers of the regularly spaced atoms of the crystals. From the electron diffraction measurement, the wavelength of matter waves was found to be 0.165 nanometer. The de Broglie wavelength lambda associated with electrons using equation 11.11 for V is equals to 54 volt is given by, you can see. Thus, there is an excellent agreement between the theoretical value and the experimentally obtained value of de Broglie wavelength. Davison-Germer experiment thus strikingly confirms the wave nature of electrons and de Broglie relation. More recently, in 1989, the wave nature of a beam of electrons was experimentally demonstrated in a double-slit experiment. Similar to that used for the wave nature of light, also in an experiment in 1994, interference fringes were obtained with the beams of iodine molecules, which are about 1,000,000 times more massive than electrons. The de Broglie hypothesis has been basic to the development of modern quantum mechanics. It has also led to the field of electron optics. The wave properties of electrons have been utilized in the design of electrons microscope, which is great empowerment with higher resolution over the optical microscope. Now the summary chapter is done. And number 1, the minimum energy needed by an electron to come out from a metal surface is called the work function of the metal, Energy greater than the work function required for electron emission from the metal surface can be supplied by suitably heating or applying a strong electric field or irradiating it by light of suitable frequency. Number 2. Photoelectric effect is the phenomenon of emission of electrons by metals when illuminated by light of suitable frequency. Certain metals respond to ultraviolet light while others are sensitive even to the visible light. Photoelectric effect involves conversion of light energy into electrical energy. It follows the law of conservation of energy. The photoelectric emission is an instantaneous process and possesses certain special feature. Third, photoelectric current depends on the intensity of incident light, the potential difference applied between the two electrodes, and the nature of the emitter material. Fourth, the stopping potential depends on the frequency of incident light and the nature of the emitter material. For a given frequency of incident light, it is independent of its intensity. The stopping potential is directly related to the maximum kinetic energy of electrons emitted. EV naught is equals to half mv square mv max square, that is k max. Fifth, below a certain frequency threshold frequency nu naught characteristic of the metal, no photoelectric emission takes place no matter how large the intensity may be. Sixth, the classical wave theory could not explain the main features of photoelectric effect. Its picture of continuous absorption of energy from radiation could not explain the independence of K max on intensity, the existence of nu naught, and the instantaneous nature of the process. Einstein explained the features on the basis of photon picture of light. According to this, light is composed of discrete packets of energy called quanta or photons. Each photon carries an energy is equals to h nu and momentum p is equals to h upon lambda, which depend on the frequency nu of incident light and not on its intensity. Photoelectric emission from the metal surface occurs due to absorption of a photon by an electron. Seventh, Einstein's photoelectric equation is in accordance with the energy conservation law as applied to the photon absorption by an electron in the metal. The maximum kinetic energy half mv max square is equal to the photon energy minus the work function of the target material. Here you can see this. This photoelectric equation explains all the features of the photoelectric effect. Millikan's first precise measurement confirmed the Einstein's photoelectric equation and obtained an accurate value of Planck's constant. This led to the acceptance of a particular of photon description nature of electromagnetic radiation introduced by Einstein. 8th, radiation has dual nature, wave and particle. The nature of experiment determines whether a wave or particle description is best suited for understanding the experimental result. Reasoning that radiation and matter should be symmetrical in nature, Louis Victor de Broglie attributed a wave-like character to matter. The waves associated with the moving material particles are called matter waves or de Broglie waves. The de Broglie wavelength associated with a moving particle is related to its momentum p, as the dualism of matter is inherent in the de Broglie relation, which contains a wave concept and a particle concept. The de Broglie wavelength is independent of the charge and nature the material particle. It is significantly measurable of the order of the atomic plane spacing in crystals. Only in case of subatomic particles like electrons, protons, etc., due to smallness of their masses and hence momenta. However, it is indeed very small, quite beyond measurement in case of macroscopic objects commonly encountered in everyday life. 10th, electron diffraction experiments by Davison and Germer and by G.P. Thomson, as well as many later experiments, have verified and confirmed the wave nature of electrons. The de Broglie hypothesis of matter waves supports the Bohr concepts of stationary orbits. Here you can see the physical quantities, their symbol, dimension, unit and remarks. So इसी के साथ ही आपका ये चैप्टर हो चुका है एंड आई होप कि ऑडियो बुक आपकी ज़रूर रिवीजन में हेल्प करेगी, तो इसको लाइक देना मत भूलिएगा एंड अपने दोस्तों के साथ भी इसे ज़रूर शेयर करिएगा